So let's say that we have a stress tensor in a coordinate system like this. Of 5, 0, -1, 0, 10, 0, -1, 0, 2. And these are in megapascals. Okay. And what we want to do is express this stress tensor in a new coordinate system that's like x this way, y this way, and z is like this. Okay, so and then we're going to draw both stress cubes. Someone asked last time about, I used to make people try to draw stress cubes at 30 and 45 degree angles and stuff, but it's pretty hard to visualize. But this is going to be easy because these are both cubes that look the same. They just have what you're calling the x face and the y face and the z face is going to be different, Are you with me on that? So we're going to go through this transformation and then redraw the stress cube. Okay, so the rotation, we're going from something like that to something like that. The z-axis is staying the same. So what rotation do you need?
90 degrees about z?
Yes, positive 90 degrees about the z-axis. And so that rotation matrix is going to be cosine of 90, sine of 90, 0, negative sine of 90, cosine of 90, 0, 0, 0, 1. Cosine of 90, that's 0. Sine of 90, 1, 0. Then negative 1, 1, 0, 0, 0, 1.
Will 1 be 0?
Yes. Thank you. And so the stress tensor in the new coordinate system is going to be 0, 1, 0, negative 1, 0, 0, 0, 0, 1. Times our original coordinate system, which is 5, 0, negative 1, 0, 10, 0, negative 1, 0, 2, times the transpose of Q. So to write the transpose, just make every row a column. So 0, 1, 0 this way, negative 1, 0, 0 this way, 0, 0, 1, like that. And what you get out of that is 10, 0, 0, 0, 5, 1, 0, 1, 2. Okay, so you get a different stress cube. You get a different stress tensor, right? But now let's think about the stress cubes. In the original coordinate system, the face on the right is the x face. The face on the top is the y face. The face facing us is the positive z. Okay. And then in the new coordinate system, it's a cube that looks like it has the same orientation. It's just the names of the faces are different. Okay. So what used to be in the original coordinate system was the positive x face. Now that's going to be the negative y face. Are you with me? What used to be the positive y is now the positive x, and the z's are going to be the same. Okay, so based on the original stress tensor, let's write these out. So on the x face, we have 5, 0, negative 1. So 5, 0 in the y direction, and 1 in the negative z. Okay? On the y face, we only have positive 10. Because of symmetry on the z face, we have this one that's positive 1. And we have 2 positive like this. Okay. Well, since these faces, you can think of this as a physical element with these loads on it, And so no matter what we call the different faces, when we go to this other coordinate system, since all of these faces line up with these, we should get something that looks exactly like this. Okay? Otherwise, the loading is different. You understand what I mean? And so what's going to happen is, when we look at the positive x face now, we expect it to say 10 this way, and that's it. Okay? So now let's read off the values that we calculated. So on the x face, we had 10 in the x direction and nothing else. This one's a little tricky because what we have is the positive y face, but that's not the one we're looking at. So remember that the negative y face is going to have exactly opposite values of the negative y face. So the negative y face says positive 5 in the y direction, and 1 in the z direction. Well, if we have, okay, so I'm just going to read the negatives of these to do the negative face. So we have 5 in the negative y direction, which is this way. And negative 1 in the z direction, which is this way. And then Z is the same. We got the 1 that way, and then the 2 that way. Okay. You can't do direct comparisons like that if the cubes are off by 20 degrees or whatever, but if they're exactly aligned like that, you could do any 90-degree rotation in any direction, and when you draw the stress cube, you get that same physical meaning back. Okay?
So you're just rotating your coordinate system, you're not rotating. Like, it's like,
Yeah.
it's like the coordinate system rotates, but the cube stays the same.
Right, exactly. Because the cube is physical, you know?
Mhm.
The cube is this infinitesimal thing that really is loaded like that. Yep.
Got it.
Okay, so now we're going to principal stresses. There's 2 kinds of principals. One is like the main thing, the boss, the guy who rules the school, you know? And the other one is like an idea, like the pleasure principle, you know? This is the main boss stress. So this is like the one at school. And the difference is you remember the principal of your school is your pal. So that's how you remember the difference between. So yeah, well, I mean, maybe not, but that's how you remember it, you know?
So this is supposed to be the principal?
Yeah, because the principal is the boss, and this is the boss stress, you know? As opposed to just like, I'm aware of the principle of this stress or whatever. That's a different thing, you know?
We're gonna go over the principles of stress later on in the course.
Exactly. I promise you not to use the other kind of principle at all in this class to try to keep it straight.
You should use it, but just mark it as secret.
Yeah, but this is the boss. This is the stress, the most important stress. That's why it's called this. Okay, and the idea of the principal stress is for any stress tensor. Did you ask me this last time? That was amazing. Someone asked me this, one of you guys, whoever it was really smart. The other one, not so much. For any stress tensor, there is an orientation
There's Joy.
What?
There's Joy, she said that.
Oh,
She asked me.
she was on fire last Friday. I have high expectations for you now.
I just didn't take my ADHD.
There's an orientation of the coordinate system where every stress element is normal. Like, why is that true? There's like no reason to think that that would be true, but it is true, you know?
That's so cool.
Yeah. So that's amazing. The stress tensor for that coordinate system is called the principal stress. That would be cool enough on its own. But wait, there's more. If you call today, this is also true of the principal stress tensor. Yeah. The greatest normal stress in this principal stress tensor is the greatest you can find in any orientation of the coordinate system. So it's the greatest for any coordinate system orientation. Comma, you're like, no, don't even try. Don't even try to tell me this. I'm not ready for this. The minimum normal stress is the minimum you can find anywhere. And by greatest and minimum, I mean in the like number line sense or whatever. So maybe they both might be negative, but the one that's the smallest negative number is going to be the greatest. The biggest negative number is going to be the minimum, you know. But the minimum normal stress in the principal stress tensor is the minimum of any coordinate system orientation.
That makes sense because it's kind of just like any other coordinate system that is represented in multiple ones of just sort of camera angle kind of.
Uh-huh.
So that would be useful in the fact that there's a limit to what your material can handle.
Yeah, so these are what you tend to use to figure out.
How strong it is.
Yeah, right.
What it's actually under. Like, look at the level two. So
Yes,
the max.
right. Yep. To see if so, this stuff is useful for figuring out like, okay, because you get this stress tensor. Like, what does it mean? You have 9 values, 6 independent values. You would just want to know, am I going to mash this material to the point that it's not going to hold anymore, you know? And this is really important for turning those 6 seemingly random values into something interpretable, you know? Well, if your principal stress tensor is all normal stresses, how many values, non-zero values, are there? 3, yep. The main diagonal is all it has, right? Of those 3 values, 1 is the maximum, 1 is the minimum. What does the middle one do? Not really anything, it's just in between those 2. It's just there, but, okay. One more thing, this is hard to word, let me think. If you rotate the coordinate system 45 degrees about the axis associated with that middle normal stress. Okay, so before I finish, let's just think about what I'm talking about. So you have a stress that only has normal stresses. Okay, so if you draw the stress cube, you have either directly out or directly in tractions on the three faces, right? And if you find the face that that's associated with the middle value of those, and you rotate your coordinate system 45 degrees about that axis, you get the stress tensor with the maximum absolute value of shear stresses. Okay, so if you rotate it 45 degrees, you're not in a principal orientation anymore. You're going to have shear stresses. And it turns out that the shear stresses you get have the biggest absolute value of any orientation you can find.
So if you rotate it 90 degrees from that axis, is it just like the negative?
If you do 90 degrees, you just get another principal stress cube again. You're just flip-flopping the meaning of the values.
With the same signs?
It depends on the coordinate system. Like if you think about this one,
Or like which direction you're flipping that face?
yeah, right. There are 6 faces, so I guess there are always there's always, I guess, 6 permutations of the principal stress tensor. Okay, but if you rotate the coordinate system 45 degrees about the axis associated with the middle normal stress, you get a stress tensor with the biggest absolute value of shear stresses.
Makes sense. That's a stress tensor. Extremely useful.
So everything, the stresses or nothing's changing, it's just how you're expressing.
Yes, exactly. It's just the coordinate system that you're looking at it in.
Yep.
Yep, that's right.
That's going to be related to our rotation matrices, right?
Yes, that's right.
So does that mean that if you're finding like what angle the coordinate system that gives it all the physical stresses, is it just always in between 0 and 90 degrees?
I think it could have combinations of different axis rotations, I'm sure. Yeah.
Because if you rotate it 90 degrees and you just get another stress tensor.
Yeah.
It's like a bit of a-
Right. But I mean, I'm sure you could have it so you have to rotate 26 degrees about this axis and then 9 degrees about this axis.
No one else thinking about a really bad middle child joke?
Yeah. Right, I understand what you mean. But that middle eigenvalue, like, is really important. He doesn't get a lot of acclaim, but he does something important here because those shear stresses are important. And want to hear something crazy?
Yes.
No one else? Everyone who doesn't, go out for 1 minute. Okay, so when you have very brittle materials, they're very prone to failing in shear. Okay, shear stresses cause brittle materials to break. The more ductile a material is, the more it's able to sort of ooze into cracks or whatever. It makes it less prone to failing in shear. But extremely brittle materials fail almost exclusively in shear. So that's true of bone, animal bone, and it's true of diamonds and whatever. So the more brittle it is, the more it fails in shear. Okay, so what happens when people get in a car accident? A lot of times their heel will hit the front of the, where the pedals are, and they'll get compression fractures in their legs. Okay, so what does a compression fracture look like? So,
Like, I took a forensic info.
oh yeah.
Class, so I'm like, wow, it's actually applying to.
Yeah, right. Okay, so this is a compression fracture of a brittle material. Well, what does the stress cube look like? You just have loading in one direction, so it looks like this, right? So this is a principal orientation, You know that's a principal coordinate system because there are no shear stresses in that orientation. Okay. So if that is a principal orientation of a coordinate, a principal orientation for this stress, how do you have to rotate this coordinate system to see what the maximum shears are? Because if this thing's brittle, it's going to break in shears.
Also, is the maximum, the minimum, and the middle are all the same values?
In this case, the minimum is this, because it's compression. The middle and the maximum are both 0.
Oh, okay.
Yep. So that can happen. You always have these 3 values, but 1 or 2 of them can be zeros.
So you just still rotate about a 0 axis?
So either you can rotate it about either axis. You can rotate it about the z-axis or the x-axis. Either one of those is fine. And the way that people like, orthopedic surgeons or whatever can tell that it was a compression fracture is because these breaks always happen like this at 45 degrees. Did you learn that in your forensics class, Joy?
Yes.
And that's why. Now you know why.
I know, she said something about, it's because of the physics or something.
Yeah.
So I'm like, I haven't got to that yet.
Yeah, well, there you go. Now you have. Go talk to her after this. That's cool, right?
Yes.
Okay. All right, so how do we calculate the principal stress? Well, we're going to use that idea of tractions. So to find the principal stress, notice that what we want is, so whatever our starting stress is, I'm just going to write out all these values. Okay, so if we're trying to identify a face where the only stress is normal, we're going to look for an outward facing normal vector that gives us a traction that's some multiple times that outward facing normal. So what we're saying is we're trying to identify a face, or we're trying to identify an axis where the traction is parallel to that axis. Okay? Like that's what it means to have a normal stress. Okay? So you can think of this as we're trying to identify a principal axis. And this is a traction on that face that's parallel to the principal axis.
Are you given lambda or do you solve for that?
We're going to have to solve for it.
So is it like multiplying it out and then doing like additional
Ye-
stuff? I don't know if you did that.
Oh, I never plugged in my computer. So, yeah, so we're going to do it once by hand, and then you're never going to have to do it like that again.
Okay.
But this, has anyone seen a problem of this form before?
Yes.
Yeah.
Yeah, this is called an eigenvalue problem.
My favorite, I hated
I know, I
this.
was like, this incited fight or flight in me for some reason.
I hated this so much.
Well, now we're just going to do it with calculators.
They
So,
were my favorite, so.
yeah,
Learned about it, but I don't remember how to do.
yeah. We're going to do one, I'm going to do one by hand so you see it, but then you're going to just do them on calculators and software. So what was, oh, I know what I was going to say. What if you got, do you remember that eigenvalues, there's no reason they have to be real, they can be imaginary.
Yeah, because it's just like,
And so what the hell would this mean if this lambda was imaginary, you know? That, we haven't talked about imaginary stresses or anything like that, right? But the good news is, this is a symmetric matrix, and symmetric matrices have real eigenvalues.
oh yeah.
Okay. So remember, lambda is always real here because the stress tensor is symmetric.
You're gonna have to pull out like how important it is. Just have to be able.
Okay, so let's go through this problem. So I'm going to write this out here. And we're multiplying that by a unit vector. And another way of writing what I have here on the right, notice that that's just exactly equal to this matrix times that unit vector. This is called the identity matrix. Well, it would be the identity matrix multiplied by that lambda. Okay.
It's like a really weird tic-tac-toe.
Yeah.
On the all of our tests, we have to solve these in by hand for the most part. Like you could check.
On tests?
Yeah.
Yeah.
No, you'll never have to do this
No,
by
I mean,
hand.
like, things
In
like
California.
Oh, yeah,
it's all
okay.
by hand.
That's why I was
Yeah.
like inciting like violence.
Right.
I'm just
No,
like-
you're going to do it with you're going to type in this matrix and call this program and it'll give you the values. Okay, so now subtract the stuff on the right from both sides and you can rewrite this in this form.
Welcome back.
Yeah, all the fight and flight instincts.
No, not even that. Like, they are kind of fun to solve.
Yeah.
at
They're
times.
not the worst.
More like the urge to go to the website I used to just solve these problems.
Yeah.
Yes, there is.
I know, right? Like, I'm
Yeah, Wolfram Alpha will do this for you.
Yeah.
Yeah.
And there's
It wasn't even that one, it was some other.
There's some
one.
Yeah.
matrix
Like,
calculator,
Yeah.
Simple, I
I
use
see.
simple as.
Hmm.
It's good.
unless you have that Raspberry Pi calculator that my friend had. You can't go on the internet for a calculator.
Okay, so so in order to find a solution to this, that matrix on the left can't be invertible.
You say something with null space and it's stuff.
Yeah, something. Yeah, right. I don't remember either. It can't be invertible. So require that the determinant is equal to 0.
So it's actually overlapping with classes required.
Except now he's about to show us how to put it in the
I
calculator.
know.
Yeah, exactly.
Yeah.
Okay, so so the determinant. So we are going to go, let's see. So the determinant, you can do it as sigma xx minus lambda times sigma y minus lambda times sigma z minus lambda minus sigma yz squared.
Wait, this,
So like first we're gonna go,
wait, is this a cross product?
no, but we're first gonna go sigma xx minus lambda times the subdeterminant of this matrix. And then we're gonna go sigma xy, actually negative sigma xy times the determinant of what's left here. So minus sigma xy times sigma xy times the quantity sigma zz minus lambda minus sigma xy This should be xz times sigma yz. And then plus sigma xz times the quantity xy, yz. So sigma xy times sigma yz minus sigma xz times the quantity sigma yy minus lambda. Okay, you'll never have to use this ever, but there's one thing that you have to recognize from this. And that is, so we want to solve this for lambda. And so the question is, what's the degree of this polynomial that we get?
Third degree.
Yeah,
There's gonna be 3 that can.
yeah, right. So it's a third degree polynomial. So there are always 3 roots.
Yeah, and sometimes it's like 0 and then like negative 1 and a pot, like,
Yeah.
like 0, negative, or and positive or something like that, right?
Mm-hmm. So it's a third degree polynomial. So there are 3 roots. And these are the 3 principal stresses.
Whoa, that's so cool.
Yeah.
This math's well, just looking.
Yeah. Now for each one of those roots, there is a corresponding unit vector nx, ny, nz. That's the eigenvector. And the 3 eigenvectors give you your principal coordinate system orientation, because those are the axes corresponding to the faces. Okay? So the 3 eigenvectors give the principal coordinate system orientation. Yeah.
Would that be the principal orientation as a vector from where your current orientation is, or?
Yeah. So it'll give you 3 vectors, 3 unit vectors, and those are vectors in your original coordinate system, and you build your new coordinate system based on those.
Okay.
Yep. And I'll go through one example by hand. Now, to solve these by hand, you have to solve a third degree polynomial. In general, that's hard to do. There's no system for that. But so how can you make a problem that's easy to solve by hand? Make sure that you only have 2 principal stresses that are non-zero. Then that polynomial reduces to a quadratic equation, and you can just use the quadratic formula to solve for it.
Mhm.
So like, I actually did used to make people do these by hand on tests way in the old days, but so how would I do it? Well, I'd sort of work backwards. I'd start with what I wanted to be my principal stresses, so that I only had 2 non-zero principal stresses, okay? Then I'd transform the coordinate system, say 25 degrees or something. I'd do some rotation, which mixes up all the values. But then I knew that that was going to reduce to a second order polynomial because that's how I had started it, you know?
Yeah.
So you were nice about it.
Yeah, I didn't make people try to flail around to solve a third order, right? So anyways, I'll go through one example of this by hand next time, and I'll also talk about different way, where you can go online or how to do it on your calculator. And then you don't really have to think about doing it by hand anymore after that. Okay, that's all.
Wait, so permanent, the math that you determine is like,